Now, one of the things that we've noticed in our solar system is, of course, um, you know, the fact that, take for example Uranus, or even Venus, for example, um, the fact that Uranus is tilted by more than 90 degrees, and of course all of its moons are going around in at that same orientation, just indicates to us that there's some kind of catastrophic event that caused this world to be leaning on its side like it is. Same goes with Venus. Why is Venus spinning upside down? There must have been some catastrophic event that caused that, and of course that has to do with all these collisions that were taking place. The planets, for the most part, form atmospheres when there's enough gravity to hold on to the atmosphere. Mars, for example, has a very light, a very low density atmosphere because it has a relatively low escape velocity. The higher the escape velocity, the thicker the atmosphere of the planets in general. All right. So one of the things that has come to light is, this is even just looking at our solar system. Um, Even before we started detecting planets around other stars, is that some people had some ideas that said, "Hey, you know what? Maybe the planets didn't exactly form where they currently are in our solar system. That there's in fact migration where the planets will actually move. Um, in some situations, the planets will move closer to the sun. In some situations, the planets will move further from the sun. That, of course, depends on interaction, gravitational interactions with other planets. Really, that's the main. Remember, most of the mass is in the sun. So now, just to let you know, when we get to other star systems, there's a lot of star systems that actually have two stars. They're called binary systems. In fact, over half the stars in our galaxy exist in binary systems. The nearest star system to our sun is called Alpha Centauri, the Alpha Centauri system, and there's actually three stars that are orbiting each other. At any rate, so that affects this idea of the migration of planets, where the planets will not, wherever they happen to have formed, they might not stay there for forever. All right. Okay. So, for example, when we believe that Jupiter began to move in towards, so it formed probably a lot further out, maybe maybe around the orbit of, who knows, but maybe be a little bit beyond Saturn, and then what happens is, as it moved in towards the sun, the as Saturn formed, and Saturn basically halted that migration in towards the sun. There's simulations that show that this is one of the possible scenarios. But one of the things that happened is, as Jupiter is the most massive planet. As it moved around, all the asteroid material and other material that was out there, like comet material, um, was flung in towards the inner part of the solar system. Now, this was very early in the history of the solar system. In fact, we call that the late heavy bombardment, which went into, in fact, most of the craters that you find on the moon. Now, there's craters that that happen on the moon all the time. Remember, the moon doesn't have any weather. It doesn't have an atmosphere. Um, but most of those craters formed during that period in the very early solar system, called the late heavy bombardment. All right, so this is this idea of Jupiter moving. There it is, the late heavy bombardment. Okay, so now this was the very first. This is called a Moa. Um, and if you haven't heard about it, it was a visitor from another solar system. Um, when it happened in 2017, there was all sorts of excitement about it. Um, it was about 300 meters long and about 30 meters in diameter. And, it's kind of a cigar shaped looking thing. Um, and, we don't know, you know, well, okay, so how do we know that this came from another star system? Um, the reason that we know that is as soon as it was detected, it was moving way too fast to be part of our solar system, right? If it was traveling, there's a certain speed that where an object, the sun has an escape velocity, right? Just like anything with mass has an escape velocity, and so if something's already has, beyond the escape velocity of the sun, when and so this thing, by the way, came in. Um, it was way out beyond the orbit of Jupiter, and that's about as close to the sun as it got. I think it's outside the solar system now, but it was moving really really fast. I don't think we can see it anymore. But when it first came in, I mean, this was made all sorts of news. Naturally, people were like, "Oh, this is going to be a spacecraft with aliens on it and stuff." It wasn't. And by the way, it was tumbling. Like it wasn't. And we sent radar signals to get a really good picture of it. That's how we know that it was 300 meters long. So like 3 football fields. Out beyond the orbit of Jupiter, and moving way too fast to be part of our solar system. And so it was just came in, got deflected a little bit by the sun's gravity, and then is on the way out. Um, all right. So so when we detected this, um, this gave us lots of speculation about, maybe things in the solar system get flung out and cross this incredible amount of distance between the stars, and will eventually, they cross what's called interstellar space. So interstellar is just in between the stars, and this object, who knows? It could have been traveling for hundreds of thousands of years between the star systems. So, all right. Anyhow, all right. So, and we don't know exactly we know what direction it came from, but it could have been deflected. If we don't even know if it came from some nearby solar system, or it's been traveling, for 10 billion years. Who knows? Um, I mean, it would have been really nice if we could have gotten a little sample of it and done a radioisotope to measure, measure the age of it. That would have been really cool. But it's really really far away now. And all right, so now we turn to exoplanets. So again, let me define that really quickly. An exoplanet is a planet orbiting another star, not our sun. All right, and so let me set the stage. It's in the 1990s. All right, so early 1990s to the mid 1990s. Basically computer technology had risen to the point where we were just barely able to um, to figure out that there were planets around other stars. All right, so here's how it goes. This was the first. So there's three methods of finding these, and they're not all equal at all. Okay, so this was the first method, and it's still used today. You can do this from ground-based telescopes, and this was the original way that this was done. All right, so now we got to turn back to Isaac Newton's third law of motion. All right, so what the third law of motion just says is for every action force, there's an equal and opposite reaction force. So let's say you have a star, this yellow one right here, and there's a planet going around the star. All right. So as the planet, so if you're observing this star from Earth, now this is the star is really far away, but if you're observing it from Earth, you don't ever see the planet directly. Okay, I want everybody to understand that. This thing called the radial method, also known as the wobble method, you don't ever see the star. But what you do see is what's called the Doppler shift. All right, a Doppler shift is the change in the wavelength. I mean, the typical Doppler shift is like if you hear an ambulance, you can always tell when the ambulance is coming towards you or moving away from you. If the pitch goes up, that means it's coming towards you. If the pitch goes down, it means it's moving away from you. And of course, the Doppler shift that works with light as well. And so the waves get pushed together, and that's called a blue shift, or the waves get more spread apart. That's called a red shift. And we do this all the time in astronomy. That's how we can measure velocities. All right. So when a planet, let's say a planet is between its star and the Earth, the star is pulled a little bit towards the Earth, so that the light would be blue shifted, and the planet is on the opposite side. Now you were assuming that the planet lines up exactly with the Earth. They don't always. In fact, they rarely line up exactly. They're usually at some bizarre angle. But anyhow, if it's on the opposite side of the star, the star is going to be pulled away from the Earth, and so that's going to give us a red shift. All right, so blue shift and then red shift, and now stars vary in brightness just naturally. Like our sun has what are called sunspots, and so if you were looking at the sun from a really distant telescope, 100 light years away or something like that, you would see variations, and you might say, oh, well, are those variations planets going around the star, or are they just, sunspots? The way that you know that that the variations are planets is when you get this periodic. So, you get these periodic signals that vary in time, with exactly the same period. Sometimes you get multiple ones because there's multiple planets going around the star, but in this case it's just a single planet going around its star will cause this wobble of the star, and only in the early 1990s, or really the mid 1990s, were we able to measure that slight wobble. So that's called the radial method. All right. Now, of course, if a planet goes around its star perpendicular to the way that we're looking at the star, right? So it's moving completely perpendicular. You're never going to see that. You're never ever going to see the radial method. All right. So, all right. So this is what we discovered. One of the very first things is we find Jupiter-sized worlds, and this was the first one. It was called 51 Pegasi. And then we've found thousands of these worlds since then. But the very first one, and a whole class of them, are called hot Jupiters. These are planets that are really close to their star, like way closer than Mercury is to our sun. And so you get these huge worlds that are